Okay, so sorry for the little delay. There's some technical difficulties. My iPad battery was completely dead, and so it's charging up. So let me give it a little time to get it charged up. But in the meantime, sorry. Okay. All right. So I'm going to have to use my computer for a while my iPad charges up, and then maybe later I can connect up to my iPad. So let me share. Okay. All right. So I hope you can all see my sharing my lecture notes on disordered metals. But before I start, and so we finished up our discussion on condo lattices last time. Are there any general questions on that? Okay, and also thanks. I think almost everyone signed up for their presentation, just a couple more people, and so we'll have a schedule fairly soon. Seems to be going pretty smoothly. And I promised you one more problem set today, but okay, I procrastinated. I'll try to get it done soon. Excuse me. All right, so we're considering today, I think for the most part, I hope you can see the arrow. Can you see the arrow?
Yes.
Okay. Just free electrons with some dispersion epsilon k moving in a random potential. V of r, which has mean 0 and root mean square value v naught squared. So among things to recall here, as we'll see, this leads to a description of transported metals where the electrons scatter randomly of the potential and undergo sort of a random walk. And because of that random walk, there's a diffusion constant and conductivity that you can define, which we'll derive today. The final result for the conductivity is the same as the Drude formula that Drude derived using a classical model of electrons. So that's a bit disappointing, but that shouldn't hide the fact that this is a very quantum process. And there are many corrections to the basic Drude result, which are highly quantum mechanical. And one of them is weak localization, and I'll say a little bit about that, I think, if not today, then in the next lecture. Okay, so we just go ahead and this is free electrons. So compared to the complexity that we've been dealing before, this is no problem at all. The only difficulty formally is one of averaging over the random potential. So the absence of translational invariance makes at least the Green's functions a little more complicated to solve. So if I just do perturbation theory, well, the perturbation theory is simply an infinite set of geometric terms like G naught, G naught V, G naught plus G naught V, G naught V, G naught, and so on. So this is the second order term, and so on. And now we just take this and term by term perform an average. So then the first order term vanishes, and the second order term gives you a non-zero value. Basically, what happens is that these two get correlated to give you a non-zero value. And then now it's no, can you see my board at the same time? I guess you can. So you get a graph like this with the G. Can you see this? Not very well. I need better colors. Okay, there's black. You can see that, I think. There's a G, and then you cross it like this. And you have to make sure that momentum is conserved. So if this is momentum K, this is K prime, then the net momentum coming through the cross has to be 0. So going this way is K minus K prime. Okay, so that has to be 0. So this is still K minus K prime. And then this means this has to be K. Okay. So the outgoing momentum is the same as the ingoing momentum. which is not the case when you first wrote it down. This was K and that was K prime. Okay. And then there are various higher order terms, which we can look at, but this will turn out to be the main term that we want to now evaluate. So if you just write this down as G naught squared for the ingoing and the outgoing legs, which have the same momentum factor of V naught squared from this, and then integral over the intermediate state K prime of G naught. The important thing here is, unlike the Feynman graphs that we met before, there's no frequency integration. The frequency is the same everywhere. And the reason is that, of course, that this potential is not time dependent. It's not an actual interaction between the electrons. I mean, graphically, it looks sort of like an interaction. If you just look at this, this looks like a photon line, maybe. But it's not really an interaction. It's just a correlation between two scattering events. And the potential is time independent. So the frequency doesn't change from this point to that point. As you can see here too, it's the same omega everywhere. So that's the difference. There's no frequency integration, there's only a momentum integration. And that's ultimately related to the fact that this is essentially coherent scattering. There's no energy loss, there's no dephasing due to different energies of the electrons. Okay. Let me see if my iPad will now connect. It's 2% charged, so maybe it will do that. So excuse me for a minute while I connect my iPad. Okay. Oh, God. There we go. Okay, it should be a second me now, hopefully, soon. All right. Okay, now I'm back to the good old way of presenting. All right, sorry for the confusion. So, right, I told you about, oh, come on. My pen is not now working. Okay, the pen needs to be recharged too. I don't know what happened. Okay. All right. Okay, so now you hopefully, yeah, that's working. Good. All right, so the higher order terms we discussed were things like this and like this, and these we can account for, but there are funny things like this that we're going to just ignore. And we could say, well, this is some kind of quantum interference effect, and if the impurities are dilute, this won't be important. That turns out to be true, but there's some subtle corrections that we'll worry about later. So if we ignore all of that, then we are just back to just putting everything in a self-energy here. And the self-energy is essentially this term right here. So what you have to evaluate is V naught squared integral over momentum K prime of the Baire-Green's function. Okay, so this is something I think we already met when we were looking at the resonant level model, the same kind of integral. And what you do is you just convert the momentum integral to an integral over energy of the density of states. and you assume the density of states is a constant, and you pull it out front. And then this integral, you can then evaluate. You multiply it by, make it a Lorentzian by multiplying it by its complex conjugate in the numerator and the denominator. So you put in a factor of minus I omega n minus E, or minus I omega n minus E. And then you can do the integral over epsilon. There's there's this term that will just give you 0 because it's an odd function of epsilon, provided the density of states is a constant. And the other one, when you do the integration, gives you an I pi out front and a sine omega n. Okay. So this is conventionally written as minus I over 2 tau. And the reason for the 2 will become clear today. And the sine omega n that you keep. And what is the definition of tau now? Tau is 2 pi times the matrix element squared times the density of states. And that's exactly Fermi's golden rule formula. If you were just computing the scattering rate of an electron off scattering of a random potential, you would just take 2 pi times the density of the matrix element squared times rho of 0. So then this is your final expression. Then for the Green's function, due to scattering, it's essentially the average Green's function is given by this. And basically what's happened is that every eigenstates, EK, seems to have a small imaginary part, which is 1 over 2 times the scattering time of the electron. And this result is actually extremely good, essentially true for all orders. As far as you're looking at the average Green's function, if you go to higher order, basically you have to replace tau by some more accurate estimate of the scattering matrix element. I mean, this is the scattering matrix element in the Born approximation. And if you want to go to higher order, you would just have to replace this by the T matrix. And once you replace by T matrix, just change the value of tau, but wouldn't change the essential structure of the Green's function. Okay. So the sine omega n is a kind of a peculiar thing, but it's a Green's function on the imaginary frequency axis, and the physical Green's function that you use to compute things on the real axis are the retarded and the advanced Green's function, and so there's the you have the complex frequency plane. The Matsubara Green's functions are defined on these points here. These are I omega n. And as the temperature goes to 0, those become a continuous set of points. Okay. But then, so what happens to this Green's function here is that this imaginary part flips sign as you go from positive frequencies to negative frequencies. And the way you can remember this is that the sign of this expression here, the self energy, has the same sign as the bare term. So when this is positive I, that's also positive I, and vice versa. And that's negative, this is negative. Okay, so then when you analytically continue, you're going to go from this point to that point. And for the retarded Green's function, you analytically continue from the upper half plane, and then you get the retarded Green's function. So if you go this way, gives you G retarded. And if you go the other way to the same frequency, you get G advanced. So because you're going in different ways, you get the opposite sign. So for the retarded Green's function, you get a plus I over 2 tau. For the advanced Green's function, you get a minus I over 2 tau. Okay, and there's also a nice way to check that. If I take the retarded Green's function and think of it as a function of omega. So here's a very well-defined function of omega. Now, where is its pole? The pole of this function is at EK minus I over 2 tau. and omega equals ek minus I over 2 tau, I get a pole. And that pole is in the lower half plane. But in the lower half plane, the Green's function, the retarded Green's function, is really the analytic Green's function in the upper half plane. So in the region where it's defined, GR, it has no pole. The pole is always in the other side, where in fact the actual physical Green's function on this side would be G advanced. So the actual Green's function that you define, the Green's function that you always work with, is something like G of Z times the integral over omega of some spectral density over omega minus Z. So that function that you use to get all the spectral rules is an analytic function of Z everywhere in the upper half plane and also the lower half plane. The only singularity it actually has is a branch cut on the real axis where the imaginary part is flip sign. So that's the physical Green's function. But the retarded Green's function does have a pole. It doesn't have a branch cut on the real axis. But once you go below the real axis, so if you keep using the wrong Green's function, if you take the upper half Green's function and go to the lower half plane, then you'll find a pole. So that's sometimes said you have it in the second Riemann sheet. Okay, just a little tirade if you get confused with these things. But that's the kind of thing that happens over and over again when you start dealing seriously with Green's functions and scattering events. Okay, so those are the average Green's function. It's very simple. There's just some scattering rate from elastic scattering. Yeah, so here I've written down the spectral form of these Green's functions from this A of k and omega. And the A of k omega that appears in these spectral forms is just a Lorentzian. And so Lorentzian with the width, which is 1 over 2 tau. Okay. All right, any questions? So we just computed the average Green's function, the presence of a potential, and nothing too surprising. So Fermi's golden rule basically tells you what happens. Okay, so now we turn to the computing something more physical. I mean, okay, this is something you could measure. It's also physical. You can measure this A of k and omega in a photo emission experiment. And if you have good momentum resolution, then you will see these Lorentzian peaks from which you can estimate the scattering time of the electrons. Okay, but now we want to compute the conductivity. All right, so here, what I haven't discussed so far is the Kubo formula for the conductivity. So this is discussed in some detail in the textbook, and I will refer you to that. But let me just give you a summary of what is the Kubo formula for the conductivity. So the Kubo formula we have, is a very general formula for linear response to any external perturbation. So in particular, we looked at the response to a change in chemical potential or some external potential, and that led to a change in the density, and that gave us the density correlation function. And we also talked about effect of a Zeeman uncoupling, and that gave us the spin-spin correlation function. So now we want to do something that measures the conductivity. And here it turns out you have to compute is the current correlation function. Not quite, but almost. And there's some subtleties which has to do with this strange way that electric current and the vector potential couples to the Hamiltonian. So let me just quickly review that, but I refer you to the book, Bruce and Flensburg, for a very nice treatment of that. So we just imagine, we'll take a very simple situation where we have a uniform electric field, which I will describe by, and I won't get all my factors of C and correct, but I don't know. Okay, minus dA dt. There's going to be some vector potential, and that gives me an electric field. And I'm going to make it frequency dependent, and I can also make it space dependent, but we assume that can be written by just in this form. And we will ignore issues associated with gauge invariance, at least to begin with. So our Hamiltonian let's just take electrons moving in free space in the Jellier model, but the same thing generalizes to electrons in a lattice too. We know that what you get is grad minus IEA squared plus terms independent of A. Okay. And then the current, the electric currents that is dHdA. And I'm going to be really sloppy about factors of 2 and signs here, but I'll get the factors 2 right. The signs I'm going to get wrong for sure. Okay, so this we can write in the following way. Oh, and there should be, of course, a psi dagger here and a psi there, and an integral over space, the minus sign out front. Okay, so the Hamiltonian, I mean the current is dHdAr, and it has 2 contributions that I'm going to separate out for our purposes. I'm going to say it's a little current, little j, and then a term that depends explicitly on A, that's going to come from here, and that's something like psi dagger psi h bar squared. There's probably yeah, okay, there's an e squared over h bar squared over m times psi dagger psi times A, where little j is the usual current h bar over 2mi. And it should be really an e, not an e squared. Oh, I don't know why I got an e. Okay. So the electric current is h bar e, h bar over 2mi. So there probably is a 1 over e here. Okay, something like that. Psi dagger grad psi minus psi grad psi dagger. Sorry, I have to keep the ordering correct. It's something like grad psi dagger psi. Yeah, okay. So that's the physical object we want to compute, the expectation value of the current J, that's the physical gauge invariant current. That's what we want to compute. And it has, one term that's independent of A. We want to evaluate this in the presence of some coupling to the external electric field. Then it has a term that's just given proportional to A. And the Hamiltonian itself, also I can expand it out. I can write that as the free Hamiltonian, integral over R, minus psi dagger h bar squared grad squared psi over 2m. And then I get a term that's proportional to A. So that'll be minus EA dot J, the little j, plus order A squared, plus terms independent of A. Okay, so now I have to compute J. So we want to compute the expectation value of A. To linear order in A. By the Kubo formula. And so what happens? So we want to compute the expectation value of J. So what I noticed that there's an expression that's 0th order in A. So if there was no electric field, the average value of this would be just 0. So, but there's a term that already depends on A. And so that term we have to keep. And we can evaluate this to 0th order in A because I'm only working to first order in A. Okay, and how does okay, so then this thing has to be computed to first order in A. So that means in the Hamiltonian, I have to compute the Hamiltonian to first order in A to figure out what's the source of any response. So the source here is just A dot J. So by the Kubo formula, then I can write the following expression. The expectation value of J, well, sometimes written as J paramagnetic plus J diamagnetic for obscure reasons. And J, what is J diamagnetic? Well, J diamagnetic is just this term over here that appears in the definition of the current. So that's turns out to be E H bar squared or H. Okay, I don't know what the factors of H bar. Yeah, I think that's correct. Expectation value of psi dagger psi evaluated in the 0th order Hamiltonian. Okay, so that's just this term, the trivial term over here. But there's also a term over here. And to evaluate this, I have to consider the response to what's in the Hamiltonian to first order in A. The Hamiltonian to first order in A is an A dot J. Okay, so therefore you conclude that it's times A here. Okay. And what's the paramagnetic response? Well, the paramagnetic response will be given by the Kubo formula. It'll be given by, well, okay, so there's an integral over some response function. I'll call it chi jj of, this is r and r minus r prime, t minus t prime of a of r prime t prime, and where chi jj is the Kubo formula expression, which is the retarded commutator of j of r and t, and j of r prime and t prime of theta of t minus t prime with a factor of, I forget, minus 1 over I or something like that. Okay, so that's the Kubo formula. You get two contributions, so it's a little more complicated than the usual case. There are two contributions to the response. There's the diamagnetic response, which is just proportional to the average value of the density. So that's trivial. That's something you know to begin with. And that has to be added to the usual Kubo response. And in the Kubo response, you have the commutator of the current. All right, so I put all that together with all the signs. And now here, capital J is what I call little j in my presentation so far. So this conductivity at frequency omega is kjj, not chi jj. So this is the way it's usually written. And kjj, the time-ordered correlation function or analytic continuation thereof for real frequencies, is the time-ordered correlation function of the current with itself, plus the diamagnetic term. And the only other surprise is this omega. What is this? Where is this omega coming from? The omega is coming from is because the response function you're interested in is j of omega is a response to some electric field, a sigma of omega times some electric field at frequency omega. Whereas what you computed is the response j to capital A. Okay. So, and how is A related to E? Well, there's the relation gives you a factor of I omega. So you have to divide the whole thing by I omega. So in practice, what happens is that, even showing that the conductivity is finite in a metal is a little tricky, because as omega goes to 0, this is blowing up. As omega goes to 0, this is going to infinity. So it better be that this expression here vanishes as omega goes to 0 in a metal. In a superconductor, it doesn't, but in a metal, in a superconductor, in fact, the entire response is the diamagnetic term, and this term just gives you 0. But in a metal, these two terms must cancel at 0 frequency. And showing that cancellation is often a bit tricky. It requires making sure you have a fully gauge invariant formalism, that the diamagnetic term cancels with the paramagnetic term. And usually people just assume it does and don't worry about it. But careful people actually check it. I'm not going to be that careful today. And unfortunately, the textbook also doesn't check it. They just go ahead and compute the real part of the conductivity. This cancellation is all purely an imaginary part of the conductivity. And so they just sidestep the issue. Well, you'll see when I sidestep it too, but there are certainly many articles that very carefully show how the paramagnetic term will cancel the diamagnetic term. Okay, so we'll just assume that diamagnetic term is there. The important point about it is just frequency independent, in fact. And therefore, it's just some constant, and it's a constant that you can safely assume is going to cancel out some other constant that would appear to make sure that as omega goes to 0, you get a finite answer. Okay, so now let's go ahead and compute this object here. Okay. So we're going to do that by diagrams. And this is the leading graph. Okay, so we just, this is the current vertex here. There's a factor of J here. There's a factor of A here. And you put let's say you put the current in the X direction. Then the operator for the current is just J sub X, H bar equals 1, Kx over M times C dagger K CK sum on K. So that's the current operator for just current flowing at 0 momentum. It's just the sum of the velocities of the electrons in the X direction summed over all electrons. Okay, so that's the operator. So associated with this vertex, you pick up a factor of K over here, Kx, and there's a factor of Kx over here. And that's what gives you this case Kx squared. There's a minus because there's a loop, and then you have the 2 Green's function. So that's the leading order term. There's some other terms that you do have to worry about in many cases, even at leading order, and the book does a more careful job about these terms. But there are terms like this. And so on. And of course, this is the fully renormalized Green's function. So graphs like this, you can ask, why didn't I include this graph? Well, that's included. This is the full G. It includes all the self energies and everything. That's the full G here. What about this term? Well, this term, at least for the model we're considering, is exactly 0. And the reason is, again, momentum conservation. So this is momentum K, this is K, this is K prime, this is K prime, and then here it's Kx, and here is Kx prime. So now the Green's function itself is an even function of K. This is an odd function of K, it's Kx. So when you do the integral over K, it gives you 0. And here, similarly, this integral also gives you 0. So when the 2 vertices have different momenta, the answer is 0, at least for the simple model we're talking about here. So this thing just equals 0. Now you can take more complicated models where there's not just S-wave scattering, as this in this model, but other angular dependent scattering. And then, of course, you have to include these graphs, and that becomes quite a job. All right. So then the current correlation function is just this bubble diagram. And this is what we have to evaluate now. Okay. So I go through in the notes a somewhat careful evaluation of it, because this Green's function, it's a kind of unusual looking Green's function, not the type that we have played much with so far. It's got this strange sine omega n over here. And when there's a sine omega n, I am a little scared about how I'm going to do the summation over the frequencies. I know how to do summation of frequencies of analytic function. This doesn't look very analytic. But I can write it as an analytic function by using the spectral representation. If I just use the Lorentzian for the spectral representation and put it in here, then the frequency of that was over here will go in the denominator. And I know how to I know how to deal with and do the frequency summation. So that's kind of what I do in the notes. I go through it very carefully. I take both Green's function and write out the spectral representation of both of them. And then I do the frequency summation of this object. That's just a familiar thing. It's I omega plus I epsilon minus some constant and I epsilon minus a constant. Just do partial fraction, and it gives you a Lindhardt function. So this frequency summation from these two terms will give me this Lindhardt function right here. No problem. Okay. And then you can proceed. So now you notice, now you've still got these two integrals to evaluate. This is not so easy. But what you notice is that if I take the first term with the Fermi function of omega 1, then the integral over omega 2 is exactly of this form. It's exactly of this form here. It's exactly of this form, and so I can go backwards and get, one of these forms, I can go backwards and get this function here. So you play tricks like that, and then when you apply this trick, you'll get the Green's function at a different frequency, plus omega in the two of them. And then you use the fact that A of k and omega is the imaginary part, which is the same as the difference between the advanced and retarded parts. And then you analytically continue this to real frequencies. And that gives you, because this is a minus here, that gives you the advanced Green's function. Because there's a plus here, you get the retarded Green's function. So it's quite a mess. And to say nothing about the diamagnetic term. And so after all of that, so this is then the final expression you get in terms of Fermi functions. And then you get these rather complicated expressions that you have to evaluate. Okay. So people do this very carefully. And what it turns out is that all these terms here that don't involve differences of the Fermi function, that really involve going far from the Fermi level. So the difficulty always is, how do you get the terms far from the Fermi level? You have to treat them very carefully to get the exact cancellation between the paramagnetic and diamagnetic terms. So these terms, involve the full Fermi function, so involve things far from the Fermi level, and they are product of G advanced, and G retarded. All the action, all the interesting stuff has to be near the Fermi level, because at low temperatures, everything is near the Fermi level, and that involves differences of Fermi functions. And that also involves advanced times retarded Green's function. And this we can evaluate now. But what I'm going to do is just get to the answer in a much quicker approach, which is how everyone does it in practice. And it's good to know how this is done. So the thing we're trying to evaluate, let's go to zero temperature right away, is something like this. There's an integral over some frequency, d. Oh, shoot. Yeah, I'm sorry. My iPad has not been charging up well at all. All right, so I'm going to have to use this behind me. Hopefully you can see it. Yeah, you can see everything, right? just make my screen, make my view bigger, and then you should be able to see it. Okay, yeah. Let's just use the board. I think it's pretty clear. Yeah. Okay. All right. So we're evaluating this graph. Just let me know if you can't see or can't hear me. Kx over here. Epsilon n plus omega n, epsilon n. So this is just k jj equals this. And so that's going to give me, I'm going to go to 0 temperature. So there's the integral d epsilon over 2 pi. And then I have the Green's functions, and there's an integral over k. And it's the same k on both of them. And it'll be something like this. I epsilon plus omega minus epsilon of k plus I over 2 tau sine epsilon plus omega times 1 over I epsilon minus ek plus I over 2 tau sine epsilon. So this is the actual expression that we have. And it looks a bit daunting when I try to do the frequency summation. And really, in all of these expressions, to get well-defined results, you do have to do the frequency summation first and then do the momentum integration. But we're going to be a little bold here. We already know that the important physics is right near the Fermi level. So we're going to convert, we're going to just focus near the Fermi level and then just do the momentum integration first, because that's a little more familiar. So how are we going to proceed with that? Well, the momentum integration, I need a little more space over here. I'm going to write the EK is just, some energy, which I'm now going to call, well, I'll just call it, let's call it Z. So there'll be integral over dz, and then I'll pull out a factor of the density of states. And so this will become Z, and this will become Z. Okay, it's the usual trick. You convert energy, convert momentum integration to energy integration with a factor of the density of states. Okay, so now I look at this expression as a function of Z. And now as a function of Z, which is the energy, not the frequency, this is actually a perfectly well-defined integral, because as Z goes to infinity, it falls off as 1 over Z squared. So I can really go all the way from minus infinity to infinity. The integral is convergent. And then what do I notice? Now, as a function of Z now, I can go to the complex Z plane. So this is a pole in energy space, not in frequency space. It's not the kind of thing you've considered before. So this has a pole when Z equals I times something. And I remember I told you that the sign of this is the same as the sign of that. So it has a pole where Z equals I times some positive number if this is positive, and and a negative number if this is negative. And the same thing is over here. Now, what happens if both this is positive and that's positive? Well, if that's the case, they'll both be up over here. And I'm doing the integration along the real Z-axis line. Now, if both poles in the same half plane, I can convert this to an integration on this side and get 0. So to get a non-zero result, I have to have the poles to be in the opposite half planes. So it has to be the case, actually they're on the imaginary axis, sorry. There has to be a pole here and a pole over here. Okay, now let's assume omega is positive. Let's take omega greater than 0, because once you have the answer for one side, you can get for the other side. And this is always bigger than that. So if this has to be, so the only possibility is that this is in the upper half plane and this is in the lower half plane. So this should be I epsilon plus omega. And this should be I epsilon. And so that tells me I can do the integral over z. And the integral over rho over E is also very much bound. The integral over E goes from minus omega to 0. Because if that wasn't the case, the poles would be in the same half plane. Only when epsilon becomes greater than 0, this pole pops out. If epsilon becomes less than minus omega, that pole comes down. And then I can do the integral. So one pole is here, one pole is here. So I'm going to close the contour in the upper half plane and pick up the contribution of this pole. So that will give me 2 pi I. And I'm going clockwise, so everything is good. And the residue will be, basically, you take the pole value, z is equal to this object, and you put it over here. So z is equal to I omega. The I epsilon will cancel with this. So this becomes I omega plus I over tau, basically. Right. Okay, so now I can, turns out to be an integral that I can evaluate. So that, the whole thing is equal to this. And so this will be equal to rho of 0. Nothing depends on epsilon, so that just gives me a factor of omega. I'm ignoring sign here. And you get 2 pi I. And I'm a little confused. Yeah, so no, it's fine. I omega plus I over tau. Okay, so that's the expression. And now let me go back to the notes and show you that that's exactly what I had from the more complicated procedure. Share screen. Right, so I showed you all of this. You can see my cursor, I hope, and everything. Right, so I went through all of these advanced and retarded Green's functions, there I got exactly this expression that's on the board, except there's no I in front of the omega. That's because that's because I've gone to real frequencies now. I have analytically continuum. Okay. All right. So now I get an expression that vanishes as omega goes to 0, provided the diamagnetic term cancels against that. So let's assume that's the case. And so I have to divide this by 1 over omega to get the conductivity. There's also a factor of 1/3. Where did the 1/3 come from? The 1/3 came from the fact in 3 dimensions, when I'm doing the integral over k, kx squared is 1/3 k squared. And then you can replace the kx squared by kf squared. Okay. So you put it all together. Now it turns out that with free electron gas, this quantity is nothing but the density, the number of electrons divided by m. And so this is the celebrated result that you get from this calculation. That's the Drude formula. I should put it up here also. And it comes from this, this contour integration that I just showed you. That's the simplest way to get it. And the notes give it to you in a more complicated way. So what we have computed is, a really important result to any experimentalist, that if you have an electric field that induces a current at this in the same direction, G of omega, these are vectors, and sigma of omega is equal to n, the density, E squared tau over m. There's no h bar anywhere, times 1 minus I omega tau. Oh, I should stop sharing, I suppose, when I'm writing on the board. Okay, so that's the famous Kubo formula. Tau, the only place tau appears really, I mean, h bar appears in the computation of tau. Otherwise, this is just the number of electrons as E, and as the mass of the electron. And this is kind of this gives you the frequency dependence. So if you plot the real part of sigma of omega, this is the kind of plot you see from optical experiments. You get what people call the Drude peak. And this value here is given by this value, and the width of this in frequency is a 1 over tau. And that's why we put in the factor of 2. So what happened was, when we did the contour integration over z, the 1 over 2 tau added with the 1 over 2 tau to give you 1 over tau. So the actual current relaxation time, or the probability relaxation time that appears in the diffusivity of the electron is 1 over tau, not the 1 over. And what appears as a pole in the Green's function is 1 over 2 tau. Roughly speaking, there's a difference between probabilities and amplitudes. So the Drude peak has a width of 1 over tau. Okay, and that's the real part. There's another interesting feature of this, is that as omega is much, much bigger than 1 over tau, the high frequency limit, sigma of omega is just NE squared. The tau will cancel out. This tau cancels with that. NE squared over minus IM omega. And that's just, you can just check, that's just Newton's laws. Newton's equation of motion. You can just get it from that because, you know, d squared x dt squared is the force, and times the E times the electric field. Just evaluate this, you'll get this conductivity. So this is just free electrons. There's no, it's purely classical. You can ignore everything. So at high frequency, there's this 1 over I omega behavior, this term here, which is just telling you that the electrons are free. Now, sometimes in materials, you don't see this 1 over I omega decay, and that indicates there's something else going on with electron-electron interactions.
Severe, I'm sorry, but could you adjust the camera for a little bit? I cannot see the.
Sorry, yeah, there you go. Okay, you can hear me, right? Okay, I'm sorry for the technical difficulties. I just didn't notice until this class. For some reason, my iPad completely discharged. Okay. All right, so where are we? No, pretty much out of time. Okay, so now let me share screen and just get started on the next topic anyway. A little bit. Okay, so this, we've derived the Kubo formula as NE squared tau over m times 1 minus I omega tau. And it's also quite general, even in cases with not just pure S-wave scattering and even strong scattering potentials. This is what you get. Okay, so this is, you know, what's sometimes called coherent transport, where there's just essentially elastic scattering of impurities and the electrons moving freely through the entire sample. And for, you know, most experimental situations, this is actually surprisingly accurate. When you go to low temperatures, we do have to worry about in some cases, when the disorder becomes very strong, you're going to get some additional quantum interference effects. So that's a huge subject on quantum transport and what are the corrections to the Kubo transport. There's a very beautiful subject of what happens in narrow wires, the whole theory of conductance through narrow wires, which actually the textbook spends quite a lot of time on. There's something called the Landauer formula for coherent transport in a narrow wire, which I won't cover. And another important phenomena that we'll talk about next time, I guess, is weak localization. This is a quantum interference effect that tells you that actually if the disorder is strong enough, eventually the electron states are going to be exponentially decaying. And weak localization is like a precursor to that. In 3 dimensions, it's just telling you that, okay, there's some corrections to conductivity, and the conductivity is actually a bit smaller than you thought from the Drude formula. And that's the first most singular correction that decreases the conductivity. Now, if that correction becomes really large, the system becomes an insulator, sometimes called an Anderson insulator. And then you get the strong localization regime. So I'll say a little bit about that tomorrow, not on next class, not too much. And then we'll go on to other topics. Okay, anyway, questions? Yes, Muji.
Hi, Sabir. I have a question. You mentioned this Drude formula requires coherent scattering. So if someone has, say, a magnetic field, would the Drude peak still centered on their frequency, or would the formula change some other shapes?
So we have derived. So you're right. I mean, I've derived the Drude formula for coherent elastic scattering. But you can also try to work with electron-electron interactions, which lead to dephasing and incoherent effects. And remarkably, in many situations, the Drude formula still works, but deriving it is a much more complicated job, and it's actually usually better done using the Boltzmann equation. If you start with the Boltzmann equation, you get a much cleaner derivation without these complicated contour integrals to worry about. And you can also generalize the Boltzmann equation for electron-electron interactions with not too much difficulty. And from that approach, you would see a bit better why the Drude formula is so universal, and where it also applies to the case where there's incoherent scattering between electrons. In fact, really, it has to, because we know it also is true in the classical.
Yeah.
Yeah.
I see. And another question is, I remember there are some mechanism that can shift the Drude peak to higher frequencies, but could you give some examples of that?
I'm not sure. Yeah, you mean I'm not sure what you have in mind. Yeah, I think people have talked about it. I don't recall, but I'm sure it involves some kind of complicated electron-electron interactions.
I see.
Which we are certainly not treating here.
I see. Thank you.
Yeah. Sure. Any other questions? Okay, so then see you on, well, there'll be a discussion session tomorrow, and Martin and others, if you want to talk about your presentation or give me a preview and comments, please feel free. Okay, see you soon.